So, good morning, all. My name is Nitin Tomar. I am a third year PhD scholar in the Department of Mathematics at IIT Bombay. Today, we are going to discuss some problems from the complex analysis. These problems will cover various topics such as singularities, meromorphic functions, poles, etc. To start with, we have the following question. So, so first of all, the question is the function sin z by z has a removable singularity at the point z equal to 0. So is the question visible?
Yes,
Yes,
sir.
sir. Yes. So we know, okay, let us revise. Okay, so we'll answer this question via the Lorentz series. Lorentz series, just a minute, let me take like this. Yes. So Lorentz series. Hmm? If like so omega, as we know, it's always be a domain. So omega in C is a domain, and Z naught belongs to omega. We fix. Now, in some neighborhood of omega, in a neighborhood, okay, not exactly neighborhood. I mean, we can take more particular. So if for Z naught, for Z belongs to B of Z naught comma R, if F has the following representation, if F has the following representation, if F has the following representation, Fz equal to, so A naught plus A1z plus so on and so forth, A2z square, no, plus A minus 1 by z plus A minus 2 by z square plus blah blah blah, which means we can write it as summation an by zn, n going from 1 to infinity, plus summation anzn, n going from 0 to infinity. So this part we know is called the principal part, and principal part is the part the which determines the nature of the isolated singularity. So if in a given in a neighborhood, if z naught is an isolated singularity, and if f can be written, if f has this following representation, which we say the Lorentz series representation, then its principal part consists of the negative powers of z. So if principal part is finite, if there is no, so only three cases are possible, right? No principal part, second is finite principal part, and third is infinite principal part, right? So there can be no other possibility for the principal part, and this is where the singularity is, the nature of singularity is decided. Okay, so we say if so, so it is about z naught. So z naught is, like, z naught is removable singularity, z naught is removable singularity, removable. Okay, I have to push it here. Z naught is removable singularity, Then if the principal part is finite, we say z naught is a pole. If there is the infinite principal part, we'll say z naught is an essential singularity. Essential singularity. So in the first question, we have been asked about sin z by z around the point z equal to 0. So first part, yes, Rajesh.
Sir, in
Sir, in
principal
principal
part,
part,
why we
why we
take
take
n
n
from
from
1?
1?
Why we
Why we
can't
can't
take
take
0?
0?
Because 0 is cover here, na? So if you take
Okay,
n
sir.
equal to 0 here, what it will be? A naught by z0, right? Which is
It
a
will
It
be
naught.
will
a
be a
naught.
note.
Yes, sir.
Yes, sir.
Okay.
Okay.
So that is cover there. Okay. Yes. So in the first question, the question is about the sin z by z. So what is the point of singularity? The point of singularity is where the function is may not be analytic. So
0.
clearly z
At
At
equal
0.
to
0.
0 is a point of singularity, right? Is a singularity. And is it an isolated singularity? Isolated, what does isolated means? You will get a neighborhood around 0. You will get a neighborhood around 0 in which there is no other singularity. And since in this case, as you can see, there is no other singularity then z equal to 0. So any neighborhood around 0, this function will be analytic, right? Is an isolated singularity. Okay. Now what kind of singularity? What kind of singularity? You know sin z has this representation. Do you know this?
Yes, sir.
Yes, sir.
Z minus z cube by 3 factorial plus z5 by 5 factorial minus blah blah blah. So if you mm, divide it by z, then what it will become? It will become 1 minus z square by 3 factorial plus z4 by 5 factorial. So does it have a singular part? Does it have a principal part? No.
No, sir.
No, sir.
So no principal part. No principal part. So this implies z equal to 0 is a removable singularity, right? So this option is correct. This option is correct. That z equal to 0 has a removable singularity. Yes. Now second is about the z sine 1 by z. So again we can use this series z sine 1 by z. So again, as you can see, z equal to 0, z equal to 0 is an isolated singularity, is an isolated singularity. Now, you try to write down the series z sine 1 by z. It will be z 1 by z minus 1 by z cube by 3 factorial. You just replace z by 1 by z, then 1 plus z by 5 times 1 by 5 factorial, and so on, so forth. So if you solve it, you will see that it will be 1 by 3 factorial z cube z square plus 1 by 5 factorial z4. So it has infinite principal part, right, Rajesh?
Yes, sir.
Yes, sir.
It's a
It's a
essential
essential
similarity.
similarity.
Exactly. Infinite principal part. So this is no principal part was it the first case. In the second case, it was infinite principal part. So this option is correct. Now, what about sine square 1 by z, cos square 1 by z? So sine square 1 by z plus cos square 1 by z. So what is the singularity here? Z equal to 0, right? Z equal to 0 is the singularity. Okay, so let me just write. So the function in this case is fz is sine square 1 by z plus cos square 1 by z. Then as you can see, z equal to 0 is the only point of singularity, hence it is an isolated singularity. It is an isolated singularity. So if z is not equal to 0, now my claim is that this is a removable singularity. So my claim is z equal to 0 is actually removable singularity. So it will be a removable singularity if and only if you can define a limit, right? That is also there in the literature. So if z is not equal to 0, if z is not equal to 0, what is the value of fz? This we have seen in the previous class. Sin square w plus cos square w is always 1. This is always 1. Okay. For z not equal to 0. So this is a constant function except at one point. So what value you would want to give? What value you would want to give at 0? So f of 0 we can define as limit z goes to 0, f of z, and z not equal to 0 here. Then it will be just 1, right? If you want to define. So this way it is a removable singularity. So this function you can define constant function 1, and that way it is a removable singularity. Is this clear?
Yes, sir.
Yes, sir.
Okay. Now, so this is false. So this option is not correct. Okay, what we can do rather than, so this option is correct. This option is correct. This option is correct. Whereas this option is false. Now, suppose f and g are holomorphic function which have removable singularities at the point z naught. Then their quotient fz by gz has a singularity. Has a which singularity? Sorry, this question is I think cut. Has a removable singularity. Yeah. No, it's not cut. Yeah, it has a removable singularity. So let us see if, so you consider these two functions fz as z and gz as z square. So these are analytic functions, right? These are actually entire functions. These are entire functions. Now what is fz by gz?
1 by
Fz
1
z.
by z.
1 by z. Does it have a removable singularity at 0? No, right? Because removable singular, see the principal part is 1 by z, right? There is a negative power of z. It does not have a removable singularity at z equal to 0. Is this clear?
Yes, sir.
See,
It
f
is.
and g, they both have removable singularity at z equal to 0, because see, because they are analytic functions. Now, but their quotient is 1 by z, which does not have a removable singularity at z equal to 0. So that option is false. Now the last option is, if f and g are meromorphic functions, if f and g are meromorphic functions of which have poles of order 3 at point z naught, then f by g has a removable singularity at z naught. Okay, so let us check. So how does any function, so what we are given, so f and g have poles of order 3 at z naught. Okay, then what can you say about f by g? Then can we say f by g has removable singularity, removable singularity at z naught? So we know if they have pole, then there is a neighborhood, there is a neighborhood or a disk for that matter, let's say bz node r, such that this f set can be written as f1z upon z minus z not cube, because it has a pole of order 3, where this f1 belongs to holomorphic function in this disk, and f1 z naught is not 0. Okay, f1 z naught is not 0. And similarly, same thing you can say for gz. Gz can also be written as g1z, z minus z naught cube, where again this g1 belongs to this space, that is g1 is holomorphic in this disk, and g1 of z naught is not 0. Then what if you divide fz by gz? What will you get? You will get f1z by gz, right? f1z by gz. So, which is, now you see at z naught, this function is analytic, right? This function is analytic at z naught. In fact, not only for z naught, we can say it for any, and f1z is not 0 for all z in this domain, and g1z is not 0 for all z in this domain. So it is a quotient of two non-vanishing analytic functions, hence it is analytic. So therefore, at z naught it has a removable singularity. Okay, so this option is true. This option is true. Now we move to the next question. This question is easy. So first of all, there is this correction that needs to be done. Hello Darshana. Hello Darshana, can you hear me? Am I audible, Darshana? Rajesh, am I audible?
Yes, sir.
Yes, sir,
Audible.
audible. So this question needs some correction. So the correction I have written. Now this says, so this function is like this: am, zm plus a m plus 1. Okay, let me write it here in the down. Okay, then we'll be able to answer this question. So fz is summation amzm, oh sorry, anzn, and n is from m to infinity, right? Now see, we don't know about m, so let us make two cases. If m is negative, so then it will be, how does it behave? It will be a m, and then it will be like this, right? I mean, so it will have, so z of so if m is negative, it means m is some minus of k, some natural number. So minus m is positive, right? See this thing, what you can write it as: a m zm plus am plus 1 zm plus 1, okay, and so on so forth. Now if m is negative, how will it look like? M is negative, so which means m is less than equal to minus 1, so it will be am upon z minus m. Minus m is positive, right?
Yes, sir.
Yes, am plus 1, then it will be minus m plus 1, right? You just replace, if you want I can replace m by minus k, because it will be of this form. Some m is fixed, m is fixed, so then it will be k plus 1. Oh god. Okay, okay. Let me do step by step. It sounds to be confusing. Okay, let us do for the first case. If m is, let's say, positive. Now, when m is positive, fz is, fz, everything is fine, right? Am, zm, because the powers will stay up because m is positive. Now, if m is negative, which means if you fix, because m is fixed, so if you fix k to be minus m, and you fix, like you write am. Hmm. Then what will be your series? Your series will be fz. It will be some coefficient am upon zk, right? Because if m is negative, so this z power m, if m is negative, so m is minus k. Now k is positive, so it will be z 1 upon zk. Okay.
But sir,
बट सर
AM में
एम
भी
में भी
चेंज
चेंज
होगा ना,
होगा ना,
AM
एम
upon Z
अपॉन
raised
जेड
to
रेस
K
टू
है
के
तो.
है तो हाँ, तो am तो okay, if you want we can write like am, you write as some bk. Okay.
Okay.
Because yeah, because bk is nothing but a of m, right? I mean, the confusion might be because this, we are playing with m and k, nothing else. Is this clear?
Yes, sir.
Yes, sir. So in the first part, that this is a positive I mean series with positive powers of z, and in the second part it is clearly a Laurent series with the negative part only, with the principal part only. And if m is 0, that case will be coming here, right? If m is 0, because it will be a naught plus, okay, let me write separately only. If m is 0, if m is 0, then what will happen? Fz will be a naught plus a1z plus a2z square, right? Now let us go to the questions now that we have. So if f has a pole of order minus m, so if m is negative, so first question is, if m is negative, then does f has a pole of order minus m?
No,
No,
sir,
sir,
because it
because
is
it is
essential
essential
singularity.
singularity.
Just a minute. Have I done something wrong? No, no. Yeah, it's correct, na? Darshana, C. So powers are getting added, right? Just a minute. Sorry. There is a bit of confusion. Okay, let us, what I want to say. So it will be some AM. Okay, let us write step by step. So when M is negative, so there will come a stage, you know, this case needs to be discussed. This M is negative is a special case which is confusing. That's it, nothing else. Yeah. Now, so what are you doing? So if M is
So we are
negative, huh?
adding a
Adding a
positive
positive
quantity to
quantity
m,
to
na?
m, na? Yes, yes.
Yes,
So
sir.
there will
After
come a
certain
stage
stage,
when you add
yes, yes,
minus M also, right?
yes, sir.
Yes, sir. Darshana, Rajesh, is this clear?
Yes, sir.
Yes, sir.
Clear,
Yes,
sir.
Clear,
sir.
sir. So it is like then after this part, everything will be positive powers, right? Positive powers of Z, right? So, and this part will give you AM by Z minus M, AM plus 1. Okay, let us just write as it is. Z uh, minus M minus 1 it will be. Not, yes, now this is correct. Plus dot dot dot, then A naught plus A1Z and so on and so forth. Is this correct? Is this fine with you guys?
Yes,
Yes,
sir.
sir. Now answer the question. So it has a pole, right? If M is negative, if M is negative, yani this case, see this case we are talking. Now, what is at zero? What is the nature? It has a finite principal part. Yes or no? This part, so this is the principal part, right? This is the finite principal part. So whenever there is a finite principal part, we know the singularity is a pole. And what is the order of the pole? The highest power of 1 by z. What is the highest power of 1 by z? It is minus m. Okay. So this option is correct actually. This option is correct. Now the question is, if f has a removable singularity at z equal to 0, if m is greater than equal to 0. So we know that when m is greater than 0, there is no singularity. When m is equal to 0, again there is no singularity, as you can see from the first and third cases. So this option is also correct. Now it says if m is greater than 0, then the function f has 0 of order m. See, you can write it as, you can write it as z power m, am plus 1, blah blah blah, right? And yeah, yes or no? So this question,
Yes,
yes,
sir.
so order at least m should be there, you know, order at least m. Because if am is 0, then you will have a order m plus 1, right? Or okay, if we assume am is 0, okay, or in this question you assume am is not 0, then only it makes oh, it is given actually am is not equal to 0. Okay, yeah, yeah. Am is not equal to 0. So if am is not equal to 0, see, you can factor this out, and this function will not have any 0 at 0, right? Because if we put z equal to 0 in the bracket function, then it will become just am, and am is not 0. So this
Yes, sir.
option should, oh shit, just a minute. So this option is correct or false? This option is correct. Now,
But sir,
but sir,
zero
zero
of
of
order
order
m, तो
m, तो
उसमें
उसमें
mth
mth
डेरिवेटिव
डेरिवेटिव
फाइंड
फाइंड
करनी होगी ना,
करनी होगी ना,
f raised
f
to
raised to
mz.
so
mz.
you try, and this mth derivative will come out am, right?
Okay,
Okay,
yes.
yes.
This
So it
am
So
is
is
it
not
not
is not
0.
equal to
equal to
zero.
0.
Exactly. So you can check that, this mth derivative at 0, it will come out to be just am, which will not be 0. Okay.
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 Yeah. Now, if f has a pole of order m greater than 0 at z equal to 0, then fk has a pole of order mk at z equal to 0. Is this correct? What do you think? See, one trivial example is, okay, so this is one thing for this question. Second is, yeah, if you take fz to be 1 by z, okay, so it has a pole, right, at 0, at 0, yes or no, of order
Yes, sir.
1.
One,
1,
yes.
yes.
Now the question is, if you take the if you take the square, if you take the power, does the order become like according to the power? For example, if you take f square, z square, so according to the question, it should be 1 square, right? The pole, the order of the pole at z equal to 0,
Two.
2.
but it is order 2, right?
Yes.
Yes.
So this option is false, right? The option given. See, because here m is 1 in our case, the example we construct, so m power k, m power square will be 1 only, right? But what we were getting was 2.
Yes,
Okay?
sir.
Yes, sir.
Yeah. Are the questions visible to you? All of you? I mean, sometimes I think, is this size fine?
Yes, sir,
Yes, sir,
fine.
fine. Now, what about say sine z by z4? What about the pole? So again, you can use that series, right? So what is sine z by z4? So the question is, oh, if sine z by z4, then m is equal to 3, not the pole. What is m? M is this uh, integer, right? M is this integer in this question. So where will this start from? So let us start. So it can be written as 1 by z4. Then first term will be z. Then z cube by 3 factorial. Then plus z5 by 5 factorial. Minus, and so on so forth. Now if you solve it, you will get 1 upon z cube minus 1 by 3 factorial z plus 1 by 3 plus z by 5 factorial. Yes or no?
Yes, sir.
Yes, sir.
So what is m? What was m? M was the coefficient where the series is starting, right? Which power
Minus
of z this
3.
series is starting? So which power of z this series is starting? It is minus 3.
Minus
Minus
3,
3,
yes.
yes.
Okay, or in this case, because oh, okay, yeah, in -3. So this option is false. But if so, you have to make sure if fz is of this form, summation a n z n, where n is from m to infinity, then m is 3, right? Sorry, then a n by z n, then m is 3. Yes or no? If what I'm trying to say is the following: a n by z n, then m is 3, because
Yes,
Yes,
sir.
sir. Yeah. Okay, so let's move to the next question. Let's move this page to trash. Yeah. Okay. Question number 3. So you know the series of Ez, right? Now this question is about, so 1 by e power 1 by z. So the point z equal to 0 is a pole of the function e power 1 by z. I think the question is small. Can you see the question now? The point z equal to 0 is a pole of the function e power 1 by z of some
Yes, sir.
factor. Okay. Now let us try to investigate what does e power 1 by z look like in its series. So e power z, how does it look? 1 plus z plus z square by 2 factorial. It has this series, right? This is for all z in C. Do all of you know that?
Yes, sir.
Yes, sir. Yeah. Okay. So V. So this is the first part. Now what will be e power 1 by z? It will be e 1 plus 1 by z 1 by 2 factorial by z square plus 1 by 3 factorial by z cube for all z not equal to 0, right? In C. Yes or no? Now, so what is, so this is at infinite principal part, right? Infinite principal part at z equal to 0. So what do you think the singularity should be z equal to 0? It should be
Essential.
essential. Exactly. So this option is false. This option is, oh, I can choose red also in this. This option is false. Okay. Now what about the next question? Okay, let's go to the fourth question first. Huh? Yeah. So if you take fz equal to z here, so f is, so the fourth question is, if f is a holomorphic function on unit disk, then the image is dense. So this option is not correct. Why? Because you take fz equal to z, the identity function, it is a holomorphic function on the unit disk, but its image will be the unit disk itself, right?
Yes,
Yes,
sir.
sir. So what is the closure of dense means? Dense in C means a set whose closure is C. So is the closure of D the complete complex plane? No. Okay. So this option is false. So okay, I'll write that, because you see the uh, later. Okay, let's go to the second question. So dense in C, first of all, okay, let's say X, a subset of C, is said to be dense in C, is said to be dense in C if X closure is the entire complex plane. Okay. For example, as an example, can you give me one example of dense set in C? Can you give one example of dense set in C? Okay, for example, you take C minus any finitely many points. Any finitely many points. This is one example. This will be dense set. What will be its closure? It will be entire C.
Yes.
Yes,
So it
so
is
it is
dense.
dense.
Yes. Next, if you take x equal to, so how does C look like? C is nothing but, like if you consider C as this, C looks like this, R plus iota times R, right?
Yes,
Money
sir.
Yes, sir.
x plus iota y, where x and y are coming from real. So if you take q plus iota q rationals, then it is dense in C, right? Because rationals are dense in real. You know this. Is this example clear?
Yes,
Yes,
sir.
sir.
Yes,
Okay,
sir.
now let's see why this function e1 by z is dense in C. So this function, let's say f, they are defining d minus 0 to C, and this is fz is e1 by z. Okay, so let let x be the range of f, x be the range set of f. What does it mean? F of d minus 0. Mm, uh, which is nothing but f of d minus 0. Range set is this only, right? Now my claim is dense means I have to show that this x closure is C. Yes or no?
Yes,
Yes,
sir.
sir.
Now, can you see that this x will be contained in C minus 0? It will never take value 0. Because exponential never takes value 0, right? As EW is never 0. It is never 0. You know this. Exponential does not take 0 as the value. Okay? Now, my claim is actually this will be an equality. So, how do you start with? You take any z in C minus 0. Okay? Now, how does it look like in polar coordinates? Then using polar coordinates, polar coordinates. How can you write z as? You can write z as r e iota theta. Yes, for some r
Yes,
Yes,
greater
sir.
than
sir.
0, because z is not 0. So this r has to be positive. Okay. Now, can you write this as exponential of r plus iota theta? Oh, exponential of ln r plus iota theta. Basically, what I have done, I have written this as E ln r plus iota theta. What it should be? E ln r times E iota theta, right? Then it will be r E iota theta, which is z. This is because. So this is correct, right? Now you choose. See, you choose any k in natural number such that modulus of this number ln r plus iota theta plus this k 2k pi is greater than 1. You can always do that, right? 2k pi iota, sorry. Yes. This you can always do. See, if this number, so see what is the mode? Mode of this will be ln r. Its mod square will be ln r square plus theta plus 2k pi square. Now you can always choose k large enough such that this is greater than 1.
Yes,
Yes,
sir.
sir.
Yeah. So this is what precisely I have written, or rather I should write it in a more better way to understand. So this, okay. Now you choose your z to be 1 upon this number ln r plus iota theta plus 2k pi I. Now what can you say about z? Is z cannot be 0, right? See, because in the denominator we have a number whose modulus is strictly greater than 1, so this z is well defined. And 1 upon some positive number is a 1 upon some non-zero number is a non-zero number, right?
Yes,
Yes,
sir.
sir.
So this z is not 0, and it is in fact d in d minus 0, because mod of mod of this number ln r plus iota theta plus 2k pi is greater than 1, so its reciprocal will have mod less than 1, right? See, if this is some alpha,
Yes, sir.
Yes, sir.
yeah. So, and what is e power 1 by z? E power 1 by z is e ln r plus iota theta plus iota 2k pi I, right? Now you know that e 2k pi I iota is 1, so it is same as e ln r plus iota theta. Oh, z will be a confusion. You just choose some z, not z we have used. Sorry. Yeah. Is this correct? Up until now, everything is clear.
Yes, sir.
Yes, sir.
Now, what is this? Okay, let me just write one more so that it's clear. And it is nothing but e ln r plus iota theta, which is z only, right? Just a minute. I have to add one page. Just a minute. Yeah. So this is clear. So you started with any c minus 0 point in c minus 0, and you show that it is in a range, right? So
Yes,
what did
Yes,
sir.
you
sir.
prove? That for any z in c minus 0, there is a point z naught in d minus 0 such that what happens, e1 by z naught is z. So what does it show? What does it show? That this range set of the range set of e1 by z, this function is nothing but c minus 0, right? Yes or no?
Yes, sir.
Yes, sir.
Okay, I am receiving a. So is this a dense set? Hello? This is dense, right?
Yes.
Yes, huh.
Which is dense in C. So this option is correct. So this option is correct. Now what about the image of this function 1 by z? This function is not dense, right?
Yes,
Yes,
sir.
sir.
Why? See, okay, let us quickly discuss. This is third option. So the function fz 1 by z in d minus 0, what will be its range? So mod f z will always be greater than 1, right? Because if z is less than for all z in d minus 0, because if mod z is less than 1, okay, let me write step by step. It is 1 by mod z, and because mod z is less than 1, so 1 upon mod z will be strictly greater than 1, right? Yes or no?
Yes.
Yes,
And therefore,
therefore,
range is
range
not
is not
C.
C.
So because no, range is not C, that is not the argument. Range set of f
Range
Range
set of
set of
F.
F.
is contained in it is contained in this set z, such that mod z is greater than 1. Yes or no?
Yes.
Yes.
So if this is my entire complex plane, and this is my open unit disk, okay, let me use some rubber. This is the boundary, I mean. So the range set is contained in which set? The range set is contained outside this set, right? Just a minute. Yes or no? Everything
Yes.
outside this. So this implies, if this is my x, if this is my x, so what will be x closure? X closure will be contained in the closure of this set, right? Z such that mod z is greater than 1. But what is the closure of this set? Closure of this set is z such that mod z is greater than equal to 1. And this is not C. So x bar is a strict subset of C. X bar is a strict subset of C. So therefore this is not dense. So this implies X is not dense in C. And for the fourth question, we know, for the fourth part, we know if you choose fz equal to z, then f of d is just d, which is not dense in C, which is not dense in C. Okay. So we are done with these questions. I mean, so what
Sir,
is?
I
I
have
have
one
one
doubt.
doubt.
Please.
अगर
अगर
F is
F is
holomorphic on
holomorphic on
C
C
minus
minus
0
zero
है,
है,
F is holomorphic on C minus
C
0.
minus
minus
0, तो
zero, तो
हम क्या
हम
बोल
क्या बोल
सकते हैं
सकते हैं
एसेंशियल
एसेंशियल
रिमूवेबल
रिमूवेबल
और
और
पोल के
पोल के
लिए?
लिए?
सिर्फ
सिर्फ
इतना ही
इतना ही
दिया है
दिया
कि
है
F
कि
is
F is
holomorphic on
holomorphic
C
on C
minus
minus
0.
zero.
Okay, then it can be anything. For example, okay, this is let us add this as remark. Okay, remark. What is your question, Darshana? F on
F
C
is
F is
minus 0.
holomorphic on
holomorphic
C
on C
minus
minus
0.
zero.
So just a minute. This is holomorphic, right?
Right.
Hmm. Now I give you some example. Okay, you consider fz equal to z, or let's say z square by z. Then it has a removable singularity at 0, right?
Removable.
Removable.
But what
What
about
about
1
1
upon
upon
F,
F,
sir?
sir?
No, I am let just give me
Okay,
some time. Okay, removable singularity at z equal to 0.
0,
Zero,
yes.
yes.
Now second is fz equal to z 1 by z, or let us say gz. Then it has pole, right, at z equal to 0,
Yes,
Yes,
sir.
sir.
or even if you want to say of order, any fixed order you want to say of order m, then what you do, you just take power m. And third, hz, it is e1 by z, then it is an essential similarity, so you cannot say anything. Okay, Darshana?
Yes.
Yes.
But
But
can we
can
say
we
1
say 1
upon f
upon
n
f
is to
vanishes to
0?
0?
1 upon f
Vanishes to
Vanishes to
0.
0.
as vanishes to 0 as z goes to 0. No,
Yes.
Yes.
vanishes means you are taking some limiting process, right? I mean, you are saying,
Yes.
Yes.
so what is the limit over?
Yes.
Yes.
So you first see that question. Okay,
Okay.
Okay.
now see in the fourth question. Okay, just give me 10 more minutes. This fancy t, we'll call it t. Okay, this is some t. T is a set of meromorphic function on omega with at least one pole, with at least one pole. Okay, then the sum of two meromorphic functions in t is always a meromorphic function in t. This option I don't think it's correct, because you take 1 by z and gz to be minus 1 by z, right? They are in t, yes or no? They have
Yes,
just
sir.
simple pole, right? But their sum is 0, which has no pole. Okay, so this option is false. Now second, what about so then f plus g does not belongs to the product. The product, what can you say about the product? That is again not correct, right? Just a minute. Okay, you can take so okay, we are taking omega to be d for all our cases, maybe. Okay, let's take z minus 1 by z and gz. Okay, let's not change. So a, where a is, and gz to be so product of two meromorphic functions in t, then we can take 1 by z and z. Yeah, we can always do this, right? You just take, let's say, 1 by 2. Yeah, then z minus 1 by 2 and z, they are in t, yes or no? They have simple pole. F has simple pole at z equal to 0 and g has simple pole at z equal to half, yes or no?
Yes, sir. Yes, sir.
But their product is 1, right? And it has no poles, whereas in t we want at least one pole, so this option is false. Now what about the question is, I think is going to be false also. Same thing you can do with the question. You just take uh, g to be 1 by g here. Oh no, what I want to say, you take fz to be z minus half by z and gz to be z minus half by z. Now these both of them are in tau, both of them have simple pole at z equal to 0, but then f by g, this is again 1, right? So this does not belongs to tau, so this option is also false. Now what about the product?